We now start chapter 6 module 2 on symmetric bilinear forms. In the previous module we have defined bilinear forms and also symmetric bilinear forms. Not only that, we have seen that X transpose AY is the model for bilinear forms, and it becomes symmetric when that matrix A is a symmetric matrix. Moreover, a symmetric bilinear form on Rn represents an inner product when we have symmetry and positive definite condition on the matrix A. We will now reach to a very important classification and prove what is called the Sylvester's law of inertia. Let F denote a field of characteristic other than 2. Let V be a vector space over F of finite dimension. The proposition: suppose that the symmetric bilinear form is not identically 0 on the vector space V over F. Then there exists a V in the vector space V such that inner product V comma V is not 0. So here we are again using the name inner product just to call that symbol, but we don't really mean that the symmetric bilinear form is an inner product. Proof: there exist V and W in the vector space V such that inner product V comma W is not 0. So if inner product VV or inner product WW is not 0, then we are done. And if not, take U is equal to V plus W. And then inner product UU is inner product V plus W comma V plus W. And then we can use bilinearity and arrive at 2 times inner product V comma W, and that is not 0. And here we have used the fact that the field has characteristic other than 2, because otherwise 2 will be equal to 0, and we cannot arrive at this result. Moreover, when we arrived at this expression that inner product V plus W comma V plus W is 2 times inner product V comma W, then we have also used the symmetry here. Now a definition. Let us start with a symmetric bilinear form on a finite dimensional vector space V over F. Now vectors V and W are said to be orthogonal if inner product V comma W is 0, and a basis consisting of the vectors V1, V2, Vn for V is said to be orthogonal if Vi comma Vj inner product is 0 for every I not equal to j, and it is said to be orthonormal if inner product Vi comma Vi is 1 for every I equal to 1 to n. Now a definition. We start with a symmetric bilinear form on V and W a subspace of V. Let us define W perp to be the set of all vectors V such that inner product V comma W is 0 for all W in the subspace W. This is called the orthogonal complement of W, and it is an easy verification that W perp defined above is a subspace of V. If we have a symmetric bilinear form on V, let us define the null space to be the set n, there is a set of all x in V such that inner product x comma V is 0 for all V in V, and a symmetric bilinear form is said to be non-degenerate if this set n is nothing but singleton 0. We have a couple of propositions which are useful and they follow easily from definitions. The first one says that let A be the matrix of a symmetric bilinear form with respect to a basis for V, then the null space n is the set of all solutions of the system of linear equations Ax equal to 0, and the form is non-degenerate if and only if A is non-singular. And the second proposition says that if we have a symmetric bilinear form on V, if W is a vector such that inner product W is not 0, if we take capital W to be the span of the vector W, then V can be written as the direct sum decomposition W direct sum W parp. And more generally, if we have a subspace W of V, and if we consider the restriction of the symmetric bilinear form on the subspace W, assuming that it is non-degenerate on W, we can write V as a direct sum decomposition W direct sum W parp. Now, a very important theorem. Suppose that F is the real field, V is a finite dimensional vector space over R, and we have a symmetric bilinear form on V. Then part 1 of the statement says that there is an orthogonal basis B consisting of the vectors V1, V2, Vn such that the inner product Vi, Vj is 0 if I is not equal to j, and inner product Vi, Vi is either 1 or minus 1 or 0. Then part 2 says, let A be an n cross n real symmetric matrix, then there exists a matrix Q in GLNR such that Q A Q transpose is a diagonal matrix such that each of its diagonal entries is 1, minus 1 or 0. And part 3 is what is known as the Sylvester's law of inertia, which says that if we write Q A Q transpose as this block where you see IP, that is the identity matrix of order P, then minus IM, that is negative of the identity matrix of order M, and then 0 Z, that is the 0 matrix of side Z, up to a permutation of the basis elements such that P denotes the number of plus 1, M is the number of minus 1, and Z is the number of 0. Then the statement says that the integers P, M and Z are uniquely determined by the bilinear form or by the matrix A, and they do not depend on the choice of the orthogonal basis B for V with inner product Vi, Vj is equal to plus minus 1. We will now prove the Sylvester's law of inertia. And what is important about Sylvester's law of inertia is that it creates invariants for a symmetric bilinear form. The invariants are those integers P, M and Z. we will see that we will be able to characterize symmetric bilinear forms on the basis of these integers. In fact, we will name them as signature, index and rank. Rank is of course the rank of the matrix. Let us now see how to prove this theorem. Proof of part 1. If the form is identically 0, then any basis of V would work. So, let us assume that the form is not identically 0. Then there exists V, let us call it V1, such that inner product V1 comma V1 is not 0. And let W denote the span of the vector V1. Then we know that V can be written as this direct sum W perp. We now restrict the form to W perp and apply induction on dimension of V. Well, W perp is a subspace of V and the dimension is strictly less than dimension of V, and therefore the induction applies. Now, if the inner product Vi is not 0 for some I, then we take 1 over Ci square is equal to plus minus inner product Vi. So, what is that supposed to mean? If inner product Vi is positive, then we take 1 over Ci square is equal to inner product Vi, and if it is negative, then we take negative of inner product Vi to be 1 over Ci square. And if we change the basis vector to Ci Vi, then we get inner product Vi is plus or minus 1. And that fulfills our requirement. Now, the part 2, given a real symmetric matrix A, we consider the symmetric bilinear form inner product xy equal to x transpose Ay and apply part 1. We know that if A is real symmetric matrix, then x transpose Ay is a symmetric bilinear form, and therefore part 1 becomes applicable on this symmetric bilinear form. Now, proof of part 3. Let V1, V2, Vn be an orthogonal basis of the type mentioned in 1, such that the matrix takes the form which is given by this block IP on the top left, that is a P cross P identity matrix, then negative of Im, that is the negative of the M cross M identity matrix, and 0 Z, that is the Z cross Z 0 matrix, and that is equal to Q A Q transpose. Now, the integer R, which is P plus M, that is the number of non-zero rows, as you can see, is the rank of the matrix, and therefore Z must be equal to N minus R. And what we are trying to prove is that these integers are invariants for the symmetric matrix or the symmetric bilinear form. That means, for any choice of basis, these numbers do not change. We first show that the integer Z is unique by showing that the set of vectors Vr plus 1 and so on up to Vn is a basis for the null space N, which is V perp. And then this will show that Z, which is n minus r, that is dimension of this null space n. Therefore, the integer z does not depend on the choice of a basis, because the null space is associated to the symmetric bilinear form, and therefore, the dimension of the null space is of course independent of the choice of basis, which would show that the integer z is independent of the choice of basis. Let W be a vector in the null space n. We know that V1, V2 and so on up to Vn is a basis, and therefore, we write W as C1 V1 plus dot 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 CR VR plus CR plus 1 VR plus 1 plus dot 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 Cn Vn. And our aim is to show that C1, C2 etc. CR, these scalars are 0, which would reduce this expression to W is equal to CR plus 1, VR plus 1 and so on up to Cn Vn, and that would prove that the set VR plus 1 and so on up to Vn is a basis for the null space n. Now, how do we get that? If we take the inner product of W with Vi, then plugging in that expression for W inside the inner product and then applying bilinearity, we obtain it is equal to Ci times inner product Vi Vi, and that is 0 for all I equal to 1 to n. But we know that inner product Vi Vi is 0 if and only if I is strictly bigger than r. Therefore, we have to have C1, C2 and so on up to Cr is equal to 0. This therefore shows that W is equal to Cr plus 1, Vr plus 1 and so on up to Cn Vn. Hence, the set Vr plus 1 and so on up to Vn is a spanning set for the null space n, and it is also linearly independent and therefore a basis for the null space n. Now, we have this relation between these integers that p plus m plus z is equal to n, and just now we have proved that the integer z is independent of the choice of basis. Therefore, the integer p plus m is also independent of the choice of basis, that is, it is determined uniquely. But we have to show that individually these integers p and m are independent of the choice of basis. And since it is not true that span of these set of vectors V1 and so on up to Vp is uniquely determined by the form, we therefore cannot immediately conclude that the integer p does not depend on the choice of the basis. That makes it difficult to prove the uniqueness of the integers p and m. Let us see how to go about it. So, suppose that V1 dash and so on up to Vn dash is another ordered orthogonal basis for V, giving rise to the integers p dash, m dash and z dash, but z dash will be z because we have proved just now that the integer z does not depend on a choice of basis. Now, our aim is to show that these vectors V1, V2 and so on up to Vp and then v dash p dash plus 1 and so on up to v dash n are linearly independent. We can see that there are precisely p plus n minus p dash of them, and if we can prove that they are linearly independent, then it would follow that p plus n minus p dash is less than or equal to n, because n is the dimension of the vector space V, and therefore, the maximum number of vectors which are linearly independent in V can be n. We therefore have p plus n minus p dash is less than or equal to n, and that implies p is less than or equal to p dash. And now if we just reverse the roles of p and p dash, we get p dash is less than or equal to p, and therefore p dash is equal to p. This will prove the uniqueness of the integer p. Let us see how to prove the linear independence of these vectors. Let us write this linear combination of the vectors v1, v2 and so on up to vp given by b1, v1 and so on up to bp, vp, and that is equal to c p dash plus 1, v dash p dash plus 1 and so on up to c n v n dash, and call it v, say. You can see that we are arriving at this kind of an expression, basic expression that b1, v1 and so on up to bp, vp minus c p dash 1 plus 1, v dash p dash plus 1 etc. up to minus c n v n dash is equal to 0. Now, let us compute the inner product v comma v in two ways. The expression v is equal to b1, v1 etc. up to bp, vp gives inner product v comma v is equal to b1 square inner product v1 comma v1 plus dot 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 bp square inner product vp comma vp, and that is equal to b1 square and so on up to bp square, which is greater than or equal to 0. On the other hand, the expression v is equal to c p dash plus 1, v dash p dash plus 1 plus dot 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 plus c n v n dash gives inner product v comma v is equal to c p dash plus 1 square inner product v p dash plus 1 comma v p dash plus 1 and so on c n square inner product v n dash comma v n dash, and finally we get minus c p dash plus 1 square minus etc. up to minus c p dash plus m dash square, and that is less than or equal to 0. It follows therefore that b1 square plus etc. bp square must be 0, and hence b1, b2 etc. up to bp is equal to 0, and this also forces c p dash plus 1 and so on up to c p dash plus m dash equal to 0, since v1 dash and so on up to vn dash is a basis. This therefore proves linear independence, and we are done. Gives us the definition of signature and rank of real symmetric bilinear forms or a real symmetric matrix, and these are invariants associated to a real symmetric bilinear form. And we often use this notation IPM to denote this block form, that is IP minus IM. For example, the Lorentz form that we saw is of the form I31. Now, let us make a couple of quick observations from Sylvester's law of inertia. One is that a real symmetric bilinear form is positive definite if and only if P is equal to n and m equal to z is equal to 0. And a real symmetric bilinear form is non-degenerate if and only if z is equal to 0. Sylvester's law of inertia gives us important invariants associated to a symmetric bilinear form or a symmetric matrix. And this actually classifies them. We will see this when we talk about classification of quadrics, and there we will be revisiting Sylvester's law of inertia. We will also see some explicit cases in terms of quadratic forms.